The nearest Earth-like world might live under a dangerous sky. Proxima Centauri, our closest star, is a violent flare dwarf. Immediate takeaway: close does not mean kind or easy. Those suns are neighbors, but the neighborhood bites hard. Today we pull back the curtain on Alpha Centauri. What looks friendly from here turns ruthless up close. Two suns band the horizon with gold and copper light. Together they anchor a triple star called Alpha Centauri. It matters because this is our most reachable other sky. One star is like our sun, a steady yellow furnace. Its partner burns smaller and warmer, an orange K-star. They dance a long ellipse, close then far, every lifetime. Swing in to about 11 astronomical units at closest approach. Drift out to around 35 astronomical units at farthest. A tiny red ember, Proxima, circles from much farther away. That third star likely loops over hundreds of thousands of years. Its distance often spans tens of thousands of astronomical units. Picture three gravities weaving lanes where planets can remain stable. Stable lanes are wider around the big pair when separations grow. The lanes shrink when the pair squeezes tight near closest approach. Around Proxima, lanes sit close to the star, hugging tight. Observers name that close region the habitable band for light. In plain words, the system is a crowded gravitational ballet. Different tempos create zones that permit or disrupt long orbits. For Alpha Centauri A, a friendly orbit sits near 1.2 AU. Around Alpha Centauri B, that ring sits near 0.7 AU. The pair's squeeze can tug distant comets toward those inner paths. Telescopes have watched their track for centuries, refining these numbers. Tiny test: imagine seasons under twin suns shifting every few decades. Net result: Alpha Centauri is close yet complex and never calm. You aim a needle across 25 trillion miles of darkness. That span defines interstellar distance between our sun and Alpha Centauri. It matters because travel time dominates every dream of visiting. With current rockets, you would need tens of thousands of years. Chemical engines top out at a few tens of kilometers per second. Nuclear concepts push faster, but still crawl compared to light. Breakthrough ideas chase fractions of light speed with reflective sails. Powerful lasers on Earth would shove a wafer craft to speed. Rule of thumb: energy demand rises with the square of velocity. Double the speed, quadruple the hit from every speck. The space between stars holds atoms, ions, and tiny dust grains. At 1/5 light speed, each grain becomes an explosive strike. A 10 micrometer grain weighs about 10 to the minus 11 kilograms. Hit that at 0.2 C, and you absorb 20,000 joules. That is a rifle shot, packed into a microscopic crater. Now scale to countless strikes over 20 years of flight. Surfaces erode, electronics glitch, and shielding mass climbs quickly. Navigation also hurts because the target moves while you chase. Alpha Centauri slides across our sky by arcseconds each year. By arrival, the alignment has shifted and windows have closed. Course corrections at relativistic speed are brutally expensive in energy. Engineers propose layered shields, sacrificial foils, and plasma plows. Example in real terms: a gram craft at 0.2 C holds about 10 to the power of 12 joules. Bottom line: distance is not empty space, it is a minefield. The sky over Proxima B can brighten like a welding arc. Proxima Centauri is a flare star, prone to violent outbursts. You should care because flares can strip and sterilize worlds. Ultraviolet and X-ray blasts hammer atmospheres, breaking molecules apart. Charged particles rake magnetic fields and currents surge into air. Close orbits keep planets tidally locked, with one face always day. Locking slows planetary rotation, which can weaken protective dynamos. Weaker dynamos mean thinner shields against relentless stellar wind. Scientists measured Proxima's outbursts across radio, optical, and ultraviolet bands. Some flares exceeded our sun's worst storms by staggering factors. Proxima B sits only 4% of Earth's distance from star. It receives about 70% of Earth's sunlight, mostly red and infrared. The heat could permit oceans, but the spectrum skews photosynthesis. Harsh flares complicate chemistry needed for delicate biology to persist. One-sentence recap: cozy light does not guarantee a cozy life. Observations confirm Proxima B's minimum mass near 1.2 Earths. Its year lasts 11 days, so dawn sweeps quickly across tide lines. If air survived, winds would howl from day toward the night. Clouds could pile at the terminator, sheltering cooler regions beneath, but repeated UV spikes can unpick ozone faster than it forms. Hydrogen escapes from split water, leaving dry rocks behind forever. Models suggest survival needs thick air and strong magnetic shielding. Even then, surface life would prefer water, ice, or caves. Quick example, one superflare could deliver 10 to the power of 25 joules across the planet's cross-section. So the picture is Proxima b might be habitable, inside armor. Turn away from the dim ember toward two steadier lights. Alpha Centauri A and B are sun-like and comparatively quiet. You care because quiet stars give biology longer, calmer windows. Their habitable rings sit farther out, at temperate starshine distances. Near star A, temperate orbits cluster near 1.2 astronomical units. For star B, temperate orbits sit near about 0.7 astronomical units. Wide binaries can shear orbits, but not near these close rings. Simulations show Earth-like orbits remain stable for billions of years. The catch is finding them, because planets here hide exceptionally well. Transits are rare, as orbital planes likely miss our line. Radial wobbles are tiny, masked by stellar noise and granulation. Direct imaging needs coronagraphs that cancel starlight to impossible precision. Engineers build instruments that chew light into sharper, cleaner pieces. Thermal cameras search for warmth where planet nightsides glimmer faintly. A mid-infrared campaign once hinted at a warm Neptune near A. That clue remains tentative, a flashing dot near instrumental limits. Meanwhile, TESS saw no clear transits around A or B. Ground spectrographs place strict limits on heavier close-in planets. Hence the best targets are Earth-mass worlds in wider orbits. Those signals require extraordinary patience and thousands of clean spectra. Example with a number, an Earth around B tugs at centimeters per second. Noise from spots and convection can be meters per second daily. One sentence recap, planets here could be calm but maddeningly elusive. Bottom line, the quieter pair may host life, yet hides it carefully. Now zoom out to icy shells far from the suns. Those shells are comet reservoirs, stirred by distant passing gravities. This matters because more impacts can reset evolving biospheres repeatedly. When A and B squeeze close, their pull shifts outer orbits. Distant bodies feel tiny kicks that add up over many loops. Perturbations can scatter comets inward, seeding heavy bombardment eras. Proxima circles even farther out, completing a loop over eons. Its long swing also nudges far belts on glacial timescales. In a triple, outer belts become restless compared to our Uit. That restlessness can spray rock and ice toward inner sanctuaries. If planets live there, impacts spike and recovery times lengthen. Meanwhile, water and organics ride in, which can help early chemistry. So the same chaos can both harm and seed potential life. Simulations show bombardment intensity waxing and waning over millions of years. In tighter phases, comet influx could rise by notable factors. When the pair widens, long peaceful stretches can return to planets. Example with numbers, the pair's orbit takes about 79 years. Their distance swings from 11 AU to 35 AU. Proxima likely orbits at tens of thousands of AU on average. Approaches near a few thousand AU may have happened in past epochs. Common mistake is imagining stability means quiet everywhere, all times. Real stability means survival through cycles, not absence of change. Net result, this neighborhood blends sanctuary with periodic hammer strikes. So the picture is, life might need patience and thick skins. Everything out there is moving, including your bullseye and background. Navigation to Alpha Centauri means predicting motion years ahead with precision. You care because a tiny miss becomes millions of kilometers later. The big pair orbit each other, shifting where planets would appear. Proxima loops around them, dragging its own wind and plasma. Your probe and their stars travel within the sun's local stream. To aim, you integrate their orbits and your acceleration in time. You also account for interstellar gas that can push and charge surfaces. Small pushes matter across decades because they drift trajectories significantly. Deep space navigation relies on pulsars, star trackers, and Doppler tones. Pulsars tick like lighthouses, letting a craft triangulate its position. Star trackers compare constellations and correct tiny orientation errors automatically. Engineers bake redundancy because dust knocks sensors offline without warning. Communications also stretch because light needs 4 years to arrive. A command today returns a reply in nearly a decade. Autonomy is required, with craft deciding when to dodge hazards. Decision trees become software, and software becomes the mission's nervous system. Example number, a 1 microradian pointing error can miss by thousands of kilometers. Thermal flexing and radiation can induce more than that without correction. Rule of thumb, plan for everything to drift, then overcorrect slightly. Edge cases swallow missions, so margins are life-saving, not optional. Bottom line, you do not aim once, you shepherd a path continuously. Approach too fast and Alpha Centauri blurs past forever. You define arrival by slowing enough to linger and observe. That matters because a flyby grants snapshots, not a neighborhood tour. Photon sails can break by leaning into starlight like wings. Magnetic sails can break by pushing against stellar wind plasma. A clever route swings by Alpha Centauri A for a turn. Photons press the sail, while gravity redirects the craft onward. Then the sail dives toward Proxima, already slower and aligned. Concept papers suggest practical fractions of light speed with braking. They trade rapid acceleration here for longer, gentler deceleration there. Sail materials need absurd reflectivity and melting points beyond current films. Guidance must twist the sail within inches at astronomical distances. Lasers on Earth must aim through air and avoid scattering. Beam riders need sensors that survive the initial furnace phase. Dust impacts at cruise still demand sacrificial edges and fields. Energy budgets balloon because you cannot regenerate a beamed push later. Another option uses onboard fuel, but mass penalties crush velocity ambitions. Hence, external power and environmental braking remain the sharpest tools. Example number 1 paper modeled arrivals within a century for gram scales. Heavier probes stretch timelines to several centuries at best. Quick check, a century there means messages start returning after 2. So plans must satisfy people who will never see results. Net result, braking is solvable in principle, but stubborn in practice. Bottom line, sprint first, then brake hard under alien light. Our nearest stars are close, but not kind or simple. Proxima flares, the big pair hides, and the void resists. Yet the path is real if we accept stubborn physics. If this changed how you see that little southern twinkle, stick around. I share new space stories every week at a human pace. See you under darker skies where difficult still feels worth it.